Hey class, today we're going to start section 3, and this section is going to be going through something called phase changes. And we're going to start with part 1 today, discussing what exactly is a phase change and what it entails. Our notes start off by saying a large iceberg contains enough fresh water to supply millions of people with water for a year. As it moves into warmer areas, this ice is going to start changing into liquid water, and eventually the ice will completely disappear and turn into liquid water. And our question that we're going to try to answer today is what happens when a substance changes from one phase to another? First, we have to understand what phase changes are and the 6 common types of phase changes. So our first key question asks us, what are the 6 common phase changes? Before we cover all 6, we need to talk about what a phase is. When at least 2 states of the same substance are present, and when I say states, I'm talking about liquid, gas, and solid. Scientists describe each different state as a phase, and a phase change is going to be reversible, which means we can undo it. It's also a physical change, which means it doesn't change what that object is made up of. All it does is change that substance from one state of matter to another. So it changes it from a liquid to a gas or a gas to a solid. Our 6 common types of phase changes are going to be melting, freezing, vaporization, condensation, sublimation, and deposition. We're going to look at this diagram that I'm going to bring up on the right, and it's going to list all 6 physical changes that can occur among a solid, a liquid, and a gas state. And they're also going to have arrows that represent which way the different phase changes are going. One thing to note and that we're going to talk about is all phase changes share certain characteristics, and we're going to relate them in terms of energy and temperature. So here are our 3 different states of matter. Again, we have solid, liquid, and a gas. And here are 6 different types of phase changes. Again, we're going to talk about melting and freezing tomorrow being opposite of each other, condensation and vaporization being opposite of one another, and sublimation and deposition being opposite of one another. One thing I like to point out is the arrow is going to show which phase that they're going between. So if something is undergoing sublimation, it's turning from a solid into a gas. If something's undergoing condensation, it's going from a gas into a liquid. And if it is freezing, it's going from a liquid into a solid. So this graph does give a brief, short definition of what these words mean. What I also want you to take note of is that there are colors for each one. We have red colors versus blue colors, and this has to do with temperature. This also is going to relate back to energy. So I'm going to be coming back to this diagram during the lesson. So what exactly happens when a substance's temperature and its energy during a phase change? One way to recognize a phase change is by measuring the temperature of a substance as we either heat it up or cool it down. And we know when a phase change is occurring because the temperature will actually level out, and the temperature does not actually change during a phase change. It will level out during that change. And I'm going to go ahead and star that because a lot of people think that we're heating it or we're cooling it, and so the temperature changes, but it actually doesn't. This graph right here is a good explanation of when we're seeing a phase change. This graph is data collected when a solid piece of naphthalene, which naphthalene is in mothballs, we're slowly heating it. The temperature at naphthalene is going to rise, and as we heat it, it's going to increase, and it's still a solid piece of naphthalene, and it's going to increase, and eventually you're going to see that it kind of like plateaus here or flattens out. When it flattens out here, it's going to flatten at a specific temperature. So here, it's going to be just above 80 degrees is when it flattens out. This point right here is when the phase change is going on. And we know that because the temperature is not changing. Once it goes from a solid and it completely changes and melts into a liquid, this is when we're going to see it start to heat back up, and now it's in its liquid state. If liquid naphthalene was cooled in reverse, the temperature will keep going down until it reaches 80, and it's going to remain 80 until all of it turns back into a solid or it freezes. And that temperature in which it freezes, we call its freezing point, is going to be identical to its melting point because they are just opposite processes of one another. So I'm going to go ahead and star that. Notice that when they freeze and melt are the same temperature. So I'm going to go back to this graph. If we were up here and we were liquid, it's going to go down, 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 down until it reaches that temperature, and it's going to freeze, and then it's going to be a solid. If liquid naphthalene is heated, its temperature keeps rising to 218 degrees Celsius until it reaches its boiling point, which is about 218, and then we're going to see another plateau as it turns into a liquid into a gas. Now that we kind of understand temperature cannot change during a phase change, what actually happens during energy? Well, during a phase change, energy is actually transferred between whatever substance we're looking at and its surroundings. So when I mean the surroundings, it could be the air, it could be something that it's touching, anything around it. The direct transfer of energy is going to depend on what type of phase change it is. So energy can either be absorbed or taken in. So if you don't know what absorbed means, it means taken in. Or it can be released or let go during a phase change. A good example of this is ice. We all seen ice. We know that it melts. We can freeze and make ice. And this is an ice sculpture of a dog sled that was carved in a winter fair in Fairbanks, Alaska. If we left this ice outside, we're going to see that it will start to melt whenever the temperature rises above 0 degrees Celsius, or you guys know this as 32 degrees Fahrenheit, which is freezing point. And the reason it's going to start to melt is because sunlight is shining directly on that ice and heating it up. So what happens is this ice is actually absorbing energy from its surroundings. It's taking energy from the sun and causing those particles to get more energy and start heating up and moving, so they're not as tightly packed as a solid. They're going to start moving and spread out and turn into a liquid. Whenever something absorbs energy, we call this an endothermic change. Endo, I think of EN, is enter, thermic is heat. So it's going to absorb energy from its surroundings, and melting is a good example of an endothermic change. In fact, 1 gram of ice will absorb about 334 joules of energy in order to melt. And we call this the heat of fusion. I will not expect you guys to know that for your test. So we know that melting is an endothermic change. So I'm going to go back to this diagram. Melting, notice, is a red color. So whenever we see red, that means it's endothermic. And that also means that we are absorbing energy. So melting is an endothermic change. We will also talk about vaporization being an endothermic change, and so is sublimation. All of these need to gain energy or absorb energy. So I would highly suggest you write this down in your notes. Now let's talk about the opposite of endothermic. Here, energy released as ice forms on these strawberry plants keeps the plant from freezing at temperatures below 0 degrees. So whenever anything goes to freezing, well, in order for particles like a liquid that are moving around to slow down and pack close together, they have to release energy. It's kind of like a kid running around and then they just zonk out. So we release this energy in the form of heat, and that's how it's cooling down. And One thing to note is 1 gram of water releases 334 joules of energy as it freezes. Again, it's the same amount as if it melts because they are opposite processes. But when water freezes, it releases heat. And this is called an exothermic change. Whenever a system releases heat, and freezing is a great example of this. So I'm going to go back to this diagram because I want you to write something else down. Freezing, notice here it has a blue arrow. So whenever we see blue, that's going to be exothermic, and that's going to be releasing energy or heat. And exo, I think of EX as like the exit. So enter and exit. And that's how I keep those two straight, and I do expect you guys to know that for your test. So again, please make sure that you guys write down red as endo, and I know your notes are in black and white, but you can outline it in a red pen or label it red. Okay. And I believe that's the end of today's lesson. If you have any questions, please make sure you ask, and I hope you guys have a great day.